Okay, so let's talk about microstructure formation during spinodal decomposition. So we had said that if we looked at the phase diagram for regular solution or such, that there was this binodal that denoted where we would have phase separation, and then there was a spinodal where the phase separation would be spontaneous, right? So if we have a system at a particular temperature and it's homogeneous, so it's at high temperature, and then we quench it down into the spinodal region, right, it's going to phase separate. And so we could ask, how does it phase separate? What does that look like? How do we describe it mathematically? And does that tell us something about the kinds of structures that form? And so here we're going to go back to thinking about the Cahn-Hilliard equation. And we're going to write down, our free energy in the case of the regular solution or similar model as a free energy per mole or per volume, which is a function of the composition, the local composition, plus a surface energy term that depends on the gradient of the composition squared. Okay, and the integral over the whole volume. So here we're saying the composition is in moles per meter cubed or some similar units. Okay, so let's think about this in 1D, right? So in 1D, we would just have G would be some area times the integral of GC plus gamma times dc dx squared times dx, right? And if we think about some fluctuation, so let's expand G about some uniform initial composition, right? Then we can think about GC as being approximated by GC0 plus the first derivative of our G evaluated at C0 times C minus C0 plus the second derivative, so 1/2 G prime prime at C0, C minus C0 squared, right? So that would be a standard Taylor expansion around C0. And now if we think about small perturbations in the composition around C0, then we would have C would be approximately equal to C0 plus some, whatever the size of the perturbation is, let's call it B, times some, let's assume it's a sinusoidal perturbation, so like cosine 2 pi x over lambda, where lambda gives us the wavelength of the perturbation, right? Or in other words, we can write this, we can define a wave vector k as 2 pi over lambda, and so oftentimes we would write this C0 plus b times cosine kx. Okay, and then our derivative dc dx would just be given by minus b times k times sine kx, right? So now if we go to calculate capital G, we get the capital G is equal to the area times the integral over the whole system times G at C0 plus G prime at C0 times C minus C0, so that would be just B cosine kx, right? Plus 1/2 g prime prime, prime prime at c0 times the second derivative, which would times c minus c0 squared, which would be b squared cosine squared kx. Okay, so this would be all from the first term, and then from the second term we would get plus gamma, and then times dc dx squared, so times b squared k squared sine squared of kx. And all this would be integrated over dx. Okay. So now we go to do this integral. So this is just a constant, so we're just going to get the volume times g at c0 for the first term, right? And then for the second term, we just have an integral over cosine, which has as many positive regions as negative regions, so that has to integrate to 0. This won't integrate to 0, so this will give us a contribution that goes like 1/4, or no, so that goes like a times 1/2 g prime prime of c0 times b squared times the integral from minus infinity to infinity of cosine squared kx dx, right? And then gamma also gives us a non-zero contribution, so that'll give us a times gamma times b squared k squared integral minus infinity to infinity sine squared kx dx. And each of these gives us a contribution of half x, so we get g is equal to v times g at c0 plus 1/4 g prime prime of c0 times b squared plus gamma b squared over 2 k squared. Okay. Or, in other words, delta g, so if we subtract off the initial, gives us vb squared over 4 times g prime prime of c0 plus 2 gamma k squared. Okay, so we can see delta g is going to be negative, right? Only under certain conditions, right? Delta g is less than 0 when so it's not sufficient that g prime prime has to be negative. It's that g prime prime at c0, so the curvature has to be less than 2 gamma k squared, right? Which is equal to 4 pi gamma over lambda. So it's only for certain lambdas, right? So this gives us a condition on lambda. So in particular, it tells us that instability only happens at particular wavelengths, and particular for lambda greater than lambda greater than 4 pi gamma over g prime prime of c0, which we'll call lambda star. So only the large wavelength modes are unstable, and only when you get above a certain length. And so this actually sets a length scale for the microstructure that forms during spinodal decomposition. And so one can actually control the wavelength of the microstructure by controlling the depth of the undercooling into the spinodal region, because that will determine the curvature of the free energy around the composition of interest. And so by quenching at different temperatures, one could get different microstructures. And this can be predicted in part using thermodynamic arguments.